so much to me. The way you kiss me, the way you squeeze me, the way you touch me.
Welcome to the video on higher derivatives. Okay, so basically, what we've studied so far is how to differentiate once. So let's say you have some function, f of x. So what we've learned is to ddx our f of x in order to get f prime of x, okay? Also known as df dx or dy dx, okay? So this is what we've been doing. This is the first derivative, okay? But there are actually many or infinite number of derivatives. So what you can do is basically you can repeatedly differentiate a function. So we could differentiate repeatedly. So here's one, okay? So here's the first one that we got, right? And then to obtain a higher derivative. So if we were to differentiate this again, so if we ddx our f prime of x, what we would get is f double prime of x, okay? And let's say we were to do it again. So we take our f double prime of x, so this is called the second derivative, all right? So this is the second derivative here. This was the first. And then this was the zero derivative. So this is our original function. So here we're at the second derivative, and let's say we ddx it again. So ddx of the f double prime of x will give you another prime there. So f triple prime of x, okay? And let's do it one more time. So if we ddx that, ddx of f triple prime of x, we get f, and then at this point we start writing a 4 instead. So the fourth derivative, because we don't want a bunch of like little tick marks up there. Okay, so you kind of get the concept. So here again, this was the second derivative, this is the third derivative, fourth, and so on. You can go on and on and on. All right. So each of these, it's important to note that ddx. So ddx, whenever you take the derivative, so this means that you differentiate once. So differentiate once. Okay. When you do this, this means that you are taking. This means the rate of change, okay? So what this signifies is a rate of change. Rate of change of whatever you are ddxing or taking the derivative of. So for example, let's say we were to have the second derivative, okay? So let's say we were to have this, which is our second derivative. This is equal to f double prime of x is equal to ddx of the first derivative, right? Okay, so that's what it's equal to. So the second derivative here, that describes the rate of change. You can replace this with rate of change, and then of whatever was inside. So rate of change of f single prime. Okay, so our second derivative here tells us how fast is our first derivative changing, okay, of our original graph. All right, so let's do some practice problems. So let's calculate. So calculate f triple prime of x of f of x is equal to 2x to the fourth minus a 3x to the third plus an 8. Okay? So let's calculate this, and the way we get to the triple prime is we have to go through the single and double primes first. So f single prime of x is going to be equal to, we bring that 4 down in front, so 2 times 4 is an 8, x to the third, okay, because we reduce the exponent by 1. We subtract a 1 away, and then we have minus 3 times, if we bring the exponent down, we get 3 times 3, so that would be a 9. Then we have x squared left, and then that plus 8 turns into a plus 0, so that just kind of goes away. All right? So now let's move on to the double prime, so the second one. So what we're going to do is basically take the derivative again. Okay, we're going to use the same rules here for derivations, for differentiation, okay? So here we're going to use the power rule, so 8 times 3 is a 24 when we bring that exponent down, and then we have a squared left in the exponent, okay? And then here we have 9 times 2, so that would be 18, and x to the 1 power. All right, so now we're almost there. We're going to make one more leap to f triple prime of x. So again, we're going to differentiate. So 24 times 2, the 2 comes down there, so 48 x to the 1 power minus an 18. Okay, so we found our answer. This is f triple prime of x. And one thing I'd like to note is that we can, so note here, we can continue continue taking the derivative, or taking derivatives, plural, until we hit 0. Okay, so let's just continue for the sake of discovery here. So f, the fourth derivative of f would equal what? So this negative 18 would go away, so all we would be left with is a 48. And then if we go one step further, take the fifth derivative, all we would get is a 0. So this is kind of another, like I said, an important discovery in that, you know how our original f of x up here, I'm going to box it now. So our original f of x was a polynomial, okay? So, and eventually, once we got to the fifth derivative, we obtained a derivative that is equal to 0. And then the sixth derivative will also equal 0, and the seventh and the eighth and the ninth, and etc., as high as you want to go. But the concept here is that with when you're working with polynomials, so polynomials, they're higher derivatives. So they're higher derivatives, higher, meaning as far as you want to go, really. Derivatives are eventually the 0 function. Eventually the 0 function. Okay, as we see here in this example, if we were to go to the 5th, 6th, 7th, 8th, 9th, etc., then we would just get the 0 function every single time. Okay?